There you go.
All right. Well, good evening, everybody. This is Gerald McKeegan again. I'm up here at the Chabot Space and Science Center. I'm up here with Richard Osier. Richard is the president of the East Bay Astronomical Society. He's also a Chabot volunteer. And between the two of us, we're going to try to do a little virtual program for you. Tonight, we were hoping to actually put cameras on the telescope and let you see some of the interesting things in the night sky. Unfortunately, Mother Nature had other ideas. So we are completely fogged in up here at Chabot. So instead of us looking through the telescope, we're going to show you some images of some of the things we were hoping to show you. And then we're going to show you how we mount different types of cameras on the telescope and show you some of the cameras that we would normally use. So what we want to do now is just kind of get started. Tonight we would have had a camera on the telescope and we would have started out by showing you a comet. So we've got some slides here. We do have some comet images and images of some of the things that we've would have been looking at. These are all images taken with this telescope. The telescope I'm using is Nellie. Nellie is our 36-inch reflecting telescope, and it's our newest telescope. And it has this nice big mirror on it, which allows us to see a lot of very faint objects out in the sky. Tonight, there is a very interesting comet up. It's got a long name. It's called C-2017 T2. It's also known as Pan-STARRS. It's named after the observatory that discovered it, the Pan-STARRS 1 observatory, which is in Hawaii on Haleakala. And it's actually fairly high up in the sky right now. It's not bright enough for you to see with the naked eye, but it would have shown up real nicely in our telescope. So wish we could have shown that to you, but best we can do is show you a picture. Another comet that I wanted to mention is a comet called SWAN. Its official designation is C-2020 F8. SWAN was discovered by an instrument on the SOHO spacecraft, which is a spacecraft that is pointed at the sun all the time. And this instrument happened to spot a comet that is now actually got quite close to the Earth. It's only about 52 million miles away from the Earth right now. If you want to get up at about 3:30 in the morning, and if you have clear skies, you might be able to see SWAN. It would be in the eastern sky, and it would be very close to the horizon. But it is a naked eye comet. It's bright enough for you to see without binoculars or a telescope or anything like that. It would be very low in the eastern sky, say around 4:30 to 5 o'clock, just before dawn, just before it gets the sky starts getting light. You might be able to see it. So you want to check that out. And that's actually going to be in the sky for the next few days. So if you're of a mind to get up at 3:30 or 4 o'clock in the morning, check it out. Okay, let's see. Our next slide is of a globular star cluster. There we go. The globular star cluster that we would have looked at first would have been M3. M3 is a globular star cluster in the constellation Boötes. It's near the bright star Arcturus. M3 is about 33,000 light years away, and it has several 100,000 stars in it. The stars in globular star clusters orbit around the center of the cluster, and then the cluster itself orbits around our galaxy. And there are about 150 of these globular star clusters orbiting around the Milky Way galaxy. And when we look at other galaxies, we see globular star clusters orbiting those as well. These stars are very old. They're among the first stars to have formed when our galaxy was forming. And they orbit not in the spiral arms of the galaxy, but in a region we call the halo, which is sort of the outer part of the galaxy. And again, these stars orbit around the center of the cluster in highly elliptical orbits. So they're very long ellipses. And they go in, get close to the center of the cluster. They're moving very fast. and then they swing out and they go way out towards the periphery of the cluster, where they're moving very slowly, and then they swing around and they come back in. We think that many of these globular star clusters have black holes at the center of them. When we look at them, and as you can see in this photograph, which was taken with Nellie, it's very dense near the center. And when we start measuring the mass of a globular star cluster and the concentration of mass, there's so much mass near that center that we're pretty sure there is a type of a black hole called an intermediate mass black hole at the center. Now, M3 would have been one of the globular star clusters that we would have looked at tonight. A little later on, we would have looked at another one, a very popular globular star cluster called M13, which is in the Hercules constellation. M13 is a very bright cluster. You can see it easily with binoculars, and on a really good clear night, you can even see it with your naked eye. And it's about 25,000 light years away. So unfortunately, we're not going to be able to see either one of those tonight. The next object we would have looked at is the Whirlpool Galaxy, M51. And here you see an image taken. This was taken by Conrad Jung. It's actually several hours of exposure time, and it's not just one long exposure. What he does is he takes multiple shorter exposures and then electronically combines them to produce a lot of detail. M51 is about 25 million light years away, and it's actually two galaxies, one feeding into the other. And this is a pretty nice image that Conrad has produced here. But a few nights ago, when we were setting up and getting ready to do this, Richard and I were up here, and we had actually at that time had a camera on the telescope, and we took some much shorter images. And so what we wanted to do is share that with you, show you what these images look like when you first get started. They're not as nice and clean and clear as what you see here. So Richard's going to switch over and show you his image that he took the other night.
And you can see that's quite a qualitative difference between this and what Conrad produced. But what Conrad produced consisted of a stack of images that look just like this. And when you take an astrophotograph using a CCD camera or a CMOS camera, the idea is to capture a whole stack of images and then put them together. And that's not an additive process, but what it is a process to increase the signal to noise ratio so that all of that gray, blotchy noise that you see across the frame that's interfering with the the spectacle of the galaxy becomes reduced as you add more and more images. So that's half of the process of producing an astro image, is all that post-processing work, stacking work, noise reduction. But this was if I remember correctly, this was a 20 or 30-second image, and then we stretched it on the screen to give you at least an idea of what it looked like in a live view.
Okay, so that's M51. We'll switch back here to our PowerPoint now. Got one other, actually two more to show you. So there's M51, the highly processed Conrad image. Conrad is a very accomplished astrophotographer. His work is so good, he's actually been exhibited at the Smithsonian Institution. So you're getting the benefit of some very professional astrophotography here done with Nellie. So the next object we were going to look at was M64, called the Black Eye Galaxy. And when you look at it, you can see it looks like it's got a little dark patch in the center, hence the name Black Eye Galaxy. This one is relatively close. It's about 17.3 million light years away. And then lastly, we were going to look at one of the galaxies in the M66 Leo triplet. In the constellation Leo, there are a lot of galaxies. and there is a group of galaxies close together called the triplet, and M66 is one of the galaxies in the triplet. It's about 27.1 million light years away. So this is just examples of some of the things we would have looked at tonight with the telescope. We would have actually put a camera on here, taken images of these, and you could actually see the process as we take more and more images. You see how they get better and better as we accumulate more and more exposures. So we're going to switch back now to the live view.
Live view of us.
Unfortunately, no live view of the night sky tonight. Mother Nature is not cooperating with it. So what we wanted to do is kind of give you an idea of some of the different ways you can take photographs through the telescope, some of the different ways we do that. There are different kinds of cameras that you can use. We'll show you several tonight. And we want to encourage you as you're watching, if you've got questions, please feel free to chime in towards the end. We'll do a little chat session and we'll be glad to answer any questions that you have. So I'm going to start out with something really basic here. This is Richard's digital SLR camera. It's a typical Canon camera. It's got a lens on the front end of it. When we want to take astrophotography or astrophotographs, the first thing we do is we take the lens off. And instead of the lens, we have a device here that's an adapter. And I got to find the...
Yeah, that's always the trick.
Where's the pin? We don't have a mark. Oh, there it is.
Yeah, there's a little dot.
Okay. All right. Okay, so we mount this on there. This is just an open hole into the camera. And we would take this and we mount it onto the telescope, tighten it up, get it lined up, and then we would take pictures. Now, if you're just going to be taking a few pictures for a few minutes, you can use the battery that's in the camera. But a lot of times we're doing long exposures. We're doing 2 or 3 minute exposures, and we're going to do maybe 20 or 30 of them over the course of a couple of hours. You can't run you on your battery doing that. So what Richard has here, and I have one too, is what we call a battery eliminator. This plugs into the camera in place of the battery, and we would then plug this into the 110 outlet, and it will power the camera for as long as we want to use it. Makes it very easy. You don't find yourself in the middle of an imaging run running out of battery. So this is just a very typical setup. This is his camera. I brought mine. It's a little slightly different adapter on here, but it's the same idea. Just mount it on the telescope and start taking pictures. Now, when you take pictures like this, and Richard's going to talk a lot more about this next week, there's a lot of things you have to do with exposure times and ISO settings and so forth, depending on what it is that you're taking photographs of. If you're taking a photograph of a moon or of the moon, then it's a relatively easy thing to do. But when you're photographing deep sky objects like galaxies, they're very faint, and it takes a little bit more technique in order to take photographs of them. So a couple of other cameras I wanted to show you here. A lot of people wonder why it is we don't just put a TV camera on the telescope and project it and do it that way. Well, we can do that, but sometimes it's pretty disappointing with what you see. There are different types of TV cameras that you can use. This is an example right here. This is just a little TV camera. There's a cable that plugs into the bottom. It goes on the telescope. For bright objects, it works great. So if you're looking at the moon, you're looking at Saturn or Jupiter or some planet like that, it works great. But when you want to look at the really faint objects, it just doesn't have the sensitivity to show you very much detail. So we rarely actually use TV cameras for anything other than planets. When we're taking pictures with the telescope, the telescope is moving. It's tracking the object that we're photographing. But no matter how well you've got the telescope tuned, it doesn't track perfectly. It tracks great if all you're doing is looking through an eyepiece at an object. But to take photographs, the telescope has to track perfectly. If it doesn't track perfectly, you take a 3-minute exposure and the telescope is drifted slightly, what you end up with is a bunch of smeared stars instead of a nice pinpoint star. So to help with that, we use a technique called auto guiding. And there are different ways of doing that. I have a little camera here that just looks like a lipstick holder. This is actually an auto guiding camera. And what we would do is we would put it on a separate telescope mounted adjacent to the main telescope. It's actually mounted on the telescope. And so it tracks with the telescope. We would mount this on it. And then there's software that will connect with this. You pick a star in the field of view of the auto guiding camera. You tell the software to track that star. The software will then watch that star, and as soon as it sees the star start to drift a little bit, it sends a signal to the telescope to reverse that drift, to stop it. And by doing that, and by making very small corrections, as soon as you see a little bit of drift, you keep the star centered in the field of view, and you get nice, sharp images when you do astrophotography. So this is one of many different kinds of auto guiding cameras.
So Gerald, so if you don't have an auto guider on Nellie, how long an exposure can you take with still getting pinpoint stars?
In most cases, we can do about 3 minutes.
Okay.
And it depends again on what we're trying to do and what kind of camera we're using. Some of the cameras have a smaller field of view, but more detail. They detect smaller changes in position. So with that, you only get maybe 1.5 to 2 minutes. With the digital SLR, you get about 3 minutes.
All right. And if you put an auto guider on, we can do 5, 10-minute exposures.
We can do an hour long.
Yeah, as long as we want. Yep.
Yeah. Okay, so these are cameras that are relatively easy to use. Digital SLR cameras, most people have some version of a digital SLR camera, but you can also take pictures with other types of commercial cameras. The one way to do that is rather than mount the camera on the telescope with no eyepiece, you take the telescope and put an eyepiece on the telescope, and then you take your camera. Now I've got another digital SLR camera here, but there are, this could be just a small power shot camera or something like that. Anything that's got the little 1/8 or 1/4 inch 20 hole at the bottom that you can thread into. This is a device which allows us to mechanically attach the camera to the eyepiece on the telescope. This is called afocal imaging. And what we do is we just hang that on there so that the lens, this is the actual lens of the camera, the lens is pointing right into the eyepiece of the telescope.
I think you slipped out.
Oh, yep, I missed it. And now you're looking with the camera into the telescope, and you focus with the camera just like you would normally, and then you can take pictures. And you get a little bit more of a magnified view doing it this way. And this is great for a lot of cameras that don't have a lens that can be removed. You can't put one of those adapters on it. There's even a version of this that works for smartphones. So there's a similar device. You mount your smartphone on it. You line it up with the lens or the eyepiece of the telescope and tighten everything up, and you can take pictures. Trying to take pictures through the eyepiece with a smartphone or any kind of a camera is just about impossible. It is so hard to get the camera lined up correctly. You have to line up the center line of your camera lens with the center line of the eyepiece. Not only that, but you can't be tipped in any direction like this.
And you have to hold it steady when you hit the
And
shutter.
you have to hold it steady while you're
Yeah.
doing all this.
I'd say what, when we have lines of people at the telescope trying to do this, I'd say 1 out of 30 people are good at it.
If that many.
Yeah.
Most of them give up after 2 or 3 minutes.
That's
They
right.
realize this isn't going to work.
I'd like to point out that on that last example you showed with the afocal camera setup, that's a perfect setup for doing planetary photography if you want to shoot photos of Mars or Jupiter or Saturn. And what you do is you actually shoot video, and you can take 2, 3, 4 minutes of video and then use software to separate all the individual frames that you shot and then stack them up just like you would take in 100 individual shots with your camera. And the results from that are fantastic.
Right.
And a lot of people are into using that exact method for doing that.
And if you have a high-end video camera, you can actually mount it just like I've mounted my digital SLR here. You just mount that camera right here. There's adjustments to the light, allows you to get everything lined up and then fire away.
Yep.
Okay, well, so these are commercial cameras, typical of what most people have, but astrophotographers and professional astronomers go a little more high-end, a little more sophisticated. So I'm going to start out with a camera that I use. If you were watching last night, you may have noticed that I talked a lot about doing asteroid work. And when I do asteroid work on this telescope, I use a very different camera. It is not a commercial digital SLR camera. It's not a color camera. It's a camera that sees only in black and white and is extremely sensitive. And this is the version that I use. Mount that on here. There's some cables that attach the camera to the computer. And you're actually controlling the camera, not here, but at the computer.
Is that one a USB camera? Does it use USB cable?
Yes,
or
yes. So it has a USB cable that goes to the computer. There's also a separate power supply for the camera. This camera is a cooled camera. So inside is a CCD chip, and behind it is what's called a Peltier cooler. That cooler will reduce the temperature down to sub-zero temperatures. And the reason you do that is the colder the chip is, the less electronic noise you get in your images. Especially when you're doing long exposure photography, you build up a lot of electronic noise on the chip if the chip is allowed to heat up. If you take your regular digital SLR camera and just open the shutter and leave it open for a while, it can do that, but the chip is actually heating up, and that produces electronic noise. With these cameras, we have a cooler inside. We cool the temperature down to -20, -30 degrees Celsius, and then we get very little noise when we do that. The camera has some capabilities that are not seen in most, well, in digital SLR cameras or commercial cameras. One important one is what we call binning. And as you know, a digital image has a bunch of pixels, little picture elements of what is what it's called, and then we call them pixels. And there's just rows and rows and rows and rows of pixels. Depending on what you're doing and how much sensitivity you want to get and how much resolution you want to get, you can do something called binning, where you take, for example, 2x2 binning. We take 2 pixels across and 2 pixels up and down, and we combine what those 4 pixels are seeing into what looks like 1 pixel. So in the final image, you see 1 pixel, but it's actually the result of 4 pixels in a 2x2 pattern. Then we can do 3x3, I've seen up to 6x6, right?
Well,
Or- and maybe
when I'm
more.
calibrating my telescope, the camera goes to 8x8.
Okay, there
So
you go.
it's
Yeah,
it's terrible looking, but it's very fast,
right,
and so it's a good way to get everything adjusted in a line.
right. Each image that you're taking with this camera, you're downloading immediately to the computer. So the camera itself is not storing the image. It's being downloaded to your computer. The more pixels you have, the longer it takes to download to the computer. Depending on what you're doing, that may or may not be an issue. But the other thing is, if you have too many pixels in your image, if you have too high a resolution, it's less sensitive. You don't, for a given length of exposure, you don't get as deep an image. You don't see as faint an object. And you get what we call oversampling. So you never want to have more resolution than you need for the type of telescope that you're using, the type of camera that you're using, and the object you're trying to image. So typically when I'm doing asteroid work with this camera, which has relatively large pixels, I've been at 2x2. And that gives me about, takes about 7 seconds to download the image. So there are different kinds. The one I use is made by Santa Barbara Instruments Group. It's one of several manufacturers of these high-end astronomical cameras. Richard's got another one over here. But one thing I should mention about this one, it shoots black and white, does not shoot in color. So if you want to shoot in color, you have to shoot through filters. Now, because I'm doing asteroid work and because this camera is more sensitive in the red part of the spectrum, I don't use filters. I just get as many photons as I can get. And you know, when we're looking for asteroids, we're looking for really faint objects. So that's ideal for that type of work. I'll show a filter wheel here. Okay.
So it's a similar type of camera. It's red, so that's a big difference. No, it's actually very similar technology to Gerald's. This is made by a company in Great Britain called Attic, and a very similarly sized chip. And it's also a monochrome camera, and it's also cooled. And you see that it's got a USB port here, same style that's used for hooking up your HP printer. But what's this here? What's this thing attached to the back? Well, that's a filter wheel. And so I've got actually seven filters in this filter wheel. One is called a luminance filter, and it basically just blocks ultraviolet light. And then I've got a red, a green, a blue, a hydrogen alpha, an oxygen 3, and a sulfur filter. Those last three are called narrowband filters, and they're looking for very specific wavelengths of light coming from deep sky astronomical objects. So for instance, a galaxy has a lot of interesting hydrogen alpha regions. A planetary nebula has a lot of interesting oxygen 3 regions, and these are wavelengths of light that are particular to those types of objects that are hard to capture without those types of filters. So what I will end up doing if I want to take a picture of, let's say, a galaxy, is I'll take a luminance shot, 5 minutes of luminance, repeat that for maybe a couple of hours, then take 20 minutes of red, 20 minutes of green, 20 minutes of blue, and put them all together, and that will give me a natural color RGB shot. If I want to enhance the image with oxygen 3, hydrogen alpha, or the sulfur filters, to be able to bring out regions in those objects that I otherwise wouldn't be able to see, then I'll take that additional shot or those additional sequence of shots and add them to the image. So getting the data for these images is half the work. Putting it together at the end is the other half of the work. So a lot of us joke that we collect our data in the summer and then process our images in the winter. So.
Yeah, you might spend 2 or 3 hours taking images at the telescope and then spend about 10 or 12 hours processing the images when you get home.
Or you get home and you realize that all of them were out of focus, and then you have to do the whole thing again.
Now one thing I wanted to mention about this camera and Richard's camera the chip in these cameras is relatively small compared to what the typical digital SLR camera has, and certainly compared to the old 35 millimeter film cameras. So the 35 millimeter frame was about that big. The chip in these cameras is maybe not quite, a little over half the that size. So the field of view of the camera is smaller than what you would have gotten with a 35 millimeter film camera. Newer cameras have larger chips. The new CMOS cameras have larger chips. And so, you know, we're getting closer and closer to being able to see the same field of view as the old 35 millimeter cameras were. But I want to show you one camera here, which does have a big CCD chip and has almost the same field of view as a 35 millimeter camera. It's a little bit older camera, but to show you this, I'm going to start out by taking the back end of the telescope off. So I've taken the whole back end of the telescope, and now I'm going to show you this. This is a camera, a filter wheel, an off-axis guider for our auto guider, and then the tube. And there we go. That is one huge, heavy camera, but it has a very wide field of view. It's a very sensitive camera. Filter wheel allows us to take pictures in different colors. This is an older camera, so doesn't have a USB interface. I think it was parallel.
It's parallel.
It's parallel. Yeah. So we don't use it anymore, but it's an example of a very high-end astronomical CCD camera. This is what professional astronomers might use.
It's kind of funny. I was thinking before we started tonight that we're showing off these CCD cameras, and I was thinking that it would be a lot like film photographers showing off their cameras in 1982. And because CCD, the whole CCD technology is going away and is being replaced with the CMOS technology that we find in our digital cameras and digital cell phones. Those are less expensive to produce. They're very easy to scale. They're not as good for science, and they're a lot noisier. So this type of technology, which was really ideal for astrophotography, is being replaced with a chip technology that is in some ways less ideal, but is made up for with better software. So it's kind of this transition that's happening in the field right now. And, you know, frankly, cameras for astrophotography has never been driven by the astronomer market. There isn't a big market of astronomers out there that influences industry to produce these cameras. For CCD imaging, it was the medical industry. And somebody said, oh yeah, these would be great for telescopes also. And so astrophotographers used CCD cameras basically because the medical industry was using CCD cameras. And now, since cell phones and cell phone cameras are so ubiquitous, the whole industry is switching to CMOS technology, and astrophotographers will have to learn to live with CMOS. That camera he put on there before, by the way, was a $45,000 camera at the time. And I was mentioning earlier that one of our friends, in fact, Kevin, who was involved in the design of this very telescope, found one on eBay for $45 and repaired it with a $3 part. And that's kind of where we're at now.
One other thing I wanted to mention, this is a typical digital SLR camera. This is Richard's Canon camera. This is an off-the-shelf camera. These cameras have a filter in them. And those filters are designed to block some of the infrared light and infrared radiation that comes from everywhere, all around us. That infrared light will tend to change how your image looks. It makes it look a little pinkish, and normally for taking portraits or landscape photos or anything like that, you don't want that. But a lot of the objects that we look at in the night sky are deep red color. They have a lot of hydrogen in them. When hydrogen is excited by any kind of energy, it emits light in a very deep red part of the spectrum. And the camera with that filter in it doesn't pick that up very well. So Canon and Nikon, I think those are the only two that did it.
Yeah, they have an astronomy camera.
Right, right. They
Really
developed
expensive.
an astronomy version of
Yeah.
this camera. So, for example, with Canon, there's the Canon 5D, and then there's the Canon 5DA. The A stands for astronomy. And what they've done is they've taken that infrared filter out of there.
Yeah, they take a part out and sell it for twice the price.
Right, exactly.
Yeah. But there's an alternative. There's a guy who you could send those cameras to Los Angeles to a company called Astrophotography, and they will surgically remove the red filter for you. And for $400, which is a fraction of the price increase for buying the astronomy version of these cameras, you can have that red filter removed. And you can still use it for daytime snapshots if you buy yourself a screw-on red filter that goes at the front of your lens. So.
All right. Well, I think we've run out of cameras to show you.
That's
so,
right.
So I think what we'll switch to is the chat line and see if there are any questions that people want to ask. And
I'll go ahead and curate some questions here and see if.
We'll do our best to answer questions.
First of all, everybody, thank you for your well wishes, and hello to everybody who said hello. And yes, the weather is lousy, and it is too bad. Alan wanted to know if you wanted to talk about cable release for shooting the photos. How do you prevent the vibration
that's a good
when you're taking a shot?
Hang on a second, I'll go grab one real fast.
Yeah. This is when I'm supposed to cue up the Jeopardy music. Ah, there he is. Yeah. There's always a gadget.
Yeah. So there are several different versions of these. I'm going to put mine on here. Actually, I've got to do it again. Okay, so this is a cable release, and it's just got a button on it. There's two ways I can do it. I can either press it and do a single exposure. I'll take a nice picture of Richard here.
There is no such thing.
Yeah, let's see. Oh. Just took a picture of Richard. So what I did is I pressed the button on the cable release, and that takes the picture. By doing that, when the camera is mounted on the telescope, you're not handling the camera. So you're not pushing the button on the camera. You're not shaking the camera. You want the camera to be as still as possible. So this is one way of doing it, using the cable release. Just take a picture like that. There are different versions of these. There's a more sophisticated one called an intervalometer. I just went the wrong direction.
Yeah, Canon sells an intervalometer. There's also a lot of companies that, a lot of people don't realize that the Canon EOS cameras also have an infrared sensor on them. And you can buy for like $10, $15 an infrared remote for the Canon cameras that will allow you to snap a picture without any cables involved at all.
Right, right.
When we're doing astrophotography with the DSLR, the software we're using to control the camera is cabled to the camera with a USB cable, and we're able to control it from our laptops. And it, in fact, usually downloads the image to the laptop as well. It doesn't even use the storage chip on the camera. So
Yeah,
it's all remote controlled under those circumstances, if you're doing that.
Yeah, I purposely didn't bring all the cables over
Yeah,
here.
yeah, it's a
because
mess.
We'd be tripping over things real
Yeah.
fast here. So, but almost all these cameras, when we're doing astrophotography, there's USB cables and power cables and so on attached to them and to the computer. And we're controlling it from the computer. The intervalometer that I mentioned before, that's a more sophisticated cable release device that you can actually program. You can tell it to take so many images, so long, how long the images should be, how much time in between each image and so forth. You can program all that into the intervalometer, set it to go and just walk away and it will do all the work for you. I've watched Conrad, he uses one quite a bit when he's doing astrophotography.
We have another question from Erica. You had mentioned that the star cluster orbits the galaxy. Do you want to talk about that? Maybe how orbits around the galaxy work?
Okay.
Yeah.
Well, if you go outside of the Milky Way galaxy or a lot of galaxies, they look like flat discs with spiral arms in them, and then they have a central bulge. Around that is a more less dense, more diffuse region we call the halo. And the globular star clusters orbit in the halo. So they're orbiting around the center of the galaxy, but they're not in the spiral arms. They may pass through the spiral arms periodically, but they're orbiting around the entire galaxy. And like I say, around the Milky Way, there are about 150 or so globular star clusters. They orbit in different directions, and they can take somewhere around 300 million years or so to orbit all the way or do one complete orbit around the galaxy.
Great. Somebody said I got here a little late. How do I start
Why?
to do, how do I, yeah, why? Yeah. How do I start to do astrophotography at home? Do you have any talks about home astrophotography? Funny you should mention that. Next week, Friday night, there will be a talk on astrophotography. Go visit the Chabot Facebook page and there will be a placeholder for it. And I hope to see you then. Somebody else asked about the telescopes at Chabot, and then somebody 2 questions down posted a link to the Chabot website for the answer to that. But you should know that we do have 3 excellent instruments here at Chabot. We have Nellie, the 36-inch research telescope that is behind me. We have Leia, which is the Alvin Clark refractor, and we have Rachel, which is the Brashear refractor, the 20-inch Brashear refractor in the big dome next to us. And once life gets back to normal and we've opened up again to the public, you'll have a chance to look through those, I hope. Any other questions? Hurry up and show us something. No, that's it. It's cloudy.
It's
There's nothing we can show you. So you have to look at us.
Yeah.
So I think that's pretty much it.
Okay,
for tonight.
well, there are no more questions.
Yeah. Thanks
Thank
for
you.
joining us, and hope you learned something.
One final thing I want to mention, here at Chabot Space and Science Center, it's a nonprofit organization. We are closed right now, which means we're getting no revenue. So we need desperately your support to keep Chabot going so that when the coronavirus shutdown is lifted, we're able to get back in business, start inviting people to come up and look through our telescopes, see all the programming and the exhibits and everything inside the museum. We really need your support to make sure that happens. So please go to the Chabot website. It's Chabot Space, all one word, chabotspace.org. And you'll see up at the top of the page, there is a donate button. Click on that button and give us as much support as you can.
Click on it many times.
Many times, yeah. All right. Okay, any other questions on there?
I think that's about it. Thank you, everyone.
All right.
See you next time.
Thanks a lot. See you later.